So this is lecture video 4 so far of the gas law. So make sure, again, as usual, make sure that you have watched 1, 2, and 3 before you actually watch this video. And in this video, I'm going to be talking about Dalton's law of partial pressure, Raoult's law, and the ideal gas law as well. So two basically, or if you can think about 3 different types of laws. Now, the Dalton's law of partial pressures is talking about pressures when there's a mixture of gases in a container. So in this case, here's a sample problem. How much pressure is exerted by this mixture of gases? And the mixture of gases in this case, there are 3 gases: oxygen at 18.2 atmospheres, nitrogen at 56.7 psi, and carbon dioxide at 21,000 pascals in a fixed container. Okay. Now, again, we have 3 different gases. These are all units of pressure, but again, there are 3 different units for pressure. So again, our goal is to change, either we change all of this into PSI, change all of this into pascals, or change all of this into ATM. I always change everything into ATMs, and the reason why that is ATMs, atmospheres, is actually the SI unit for pressure. Okay, not PSI, not pascals. Actually, it's pascals, actually, the unit if you want to think about it that way. But for gas laws, in the gas constant, the unit for pressure is ATM. So I always go that way. So I'm going to convert 56.7 psi into ATMs. So again, this conversion is actually, again, in your exam reference sheet. Unit conversion, you want the unit that's given to you as the same unit at the bottom. Cancel. Same thing for pascals. So this is 0.21 ATM. And then at the end, you just add them all together. Now, obviously, if this were 3 different units, if you remember from algebra, you cannot add 3 numbers that have 3 different units anyway. So again, this is one of the reasons why we are making sure that all of the units are the same. Again, it wouldn't matter again if everything was in ATM, everything is in PSI, or everything is in pascals. But in this case, I just chose to change all the units into ATMs. So the total pressure exerted by all of these 3 gases is just, in this case, the sum of all of their pressures. And the reason why this is, again, based upon the kinetic molecular theory. And the kinetic molecular theory states that gas particles do not interact with each other. This gas does not inhibit the pressure of this gas, and this gas does not affect the pressure of this gas and this gas. So all of them will react like there's no other gases present in a container. And that is why we add them, okay, because it seems like they're all doing their own thing. Okay, so obviously in this case, if you have 3 different gases with 3 different pressure, you will add them, and the total pressure is shown here, 22.3 ATM. An offshoot of Dalton's law of partial pressure is Raoult's law. And Raoult's law says that all of them, okay, if you add all of their proportions based on their pressure should be equal to 1 or 100%. Okay, and that's again, you can predict the molar ratio of its gas in the container. And the way you do this is you take each individual gas and you divide it by the total pressure. So for O2, it'll be 18.2 divided by the total pressure, 22.3. For nitrogen, it'll be 0.21 ATM. Actually, that's not nitrogen, that's actually carbon dioxide. Okay, this is again 0.21 ATM divided by 22.3, and then nitrogen is 3.86 divided by 22.3. If you add all of these things together, 0.82 plus 0.17 plus 0.0094, the answer, because I did some rounding, is going to be 0.999, which is 1 or 100%. Okay, so very, very important here. So that is basically the Dalton's law of partial pressures and Raoult's law. Now we're going to be talking about a much more complex law called the ideal gas law. All right. So in the ideal gas law, and the ideal gas law is actually shown by PV equals nRT. What is actually shown here is you actually have volume, you have temperature, and you have pressure. All right, and we're asking for moles. In a previous, we already done some cases in which we actually already covered some moles. Avogadro's law is one of them, which is volume over number of moles. But in this case, as you can see, we're looking for N, and we have a volume, we have a temperature, and we have a pressure. So if I rewrite the whole ideal gas equation, since there's only one volume, only one temperature, and only one pressure, right? One side of the equation gets eliminated. And again, we have P1 over V1 equals nRT equals 0. So in this case, we need to rearrange the equation to equal the unknown. All right, so we are trying to find n. Okay, and that's how we actually come up with this equation, PV over RT equals n. If you are confused with this one, this is algebra again. What you do is you go like this, right? nRT, right? And again, if I need to isolate n by itself, I just divide both sides by RT. Again, this is why the prerequisite for this class is algebra. And again, the R gets canceled, the T gets canceled, and you just have n on one side and everything else on the other side, which is the same as this. Now here's the deal. Here's a problem. The R, which is the gas constant, is 0.0821. That's a number. But it also has this highly specific units. It has the unit of volume has to be in liters. The unit for pressure has to be in ATMs, and the unit for temperature has to be in Kelvin. That means to say this has to be changed into Kelvin, and this has to be changed into ATM. Right? This is fine. This is radian liter. So all the units have to match up the units in the gas constant when you use the ideal gas equation. So we're going to convert the Celsius into Kelvin, which is just an addition. 25 plus 273 is 298 Kelvin. And then we're just going to change the 20 psi into ATM. 20 psi, again, conversion divided by 14.7 is 1.36 ATM. Check. Check. Chug and plug. Now here's the deal. You need to make sure that you insert this in parentheses, you go 1.36 times 2.2 divided by, open parenthesis, 0.0821 times 298, close the parenthesis, equals, and the answer is 0.12 moles. Okay, so there are 0.12 moles for a gas at these conditions, at this volume, at that temperature, and at that pressure. Okay, so that's called the ideal gas equation. Now the ideal gas equation, just to give you a clue, and not to give you a clue, but just as an overview again, is ideal gases are only true, the behavior for ideal gases is only true when you have a very, very, very low temperature. Actually, not very, very low temperature, I'm sorry. High temperature, okay, and high volume, right? And the reason why is this behavior is based upon primarily about temperature. So what happens is, if you freeze, if you go all the way down to such a low temperature, what happens is the gases now, in this case, will now, because one of the postulates of the kinetic molecular theory is gases have high kinetic energy. Well, at absolute zero, which is 0 degree Kelvin, gases don't move anymore. All right. So in this case, this is the reason why we cannot use this the ideal gas behavior for extremely low temperatures. And when we're talking about extremely low temperatures, we're actually going to be talking about something close or even something past absolute zero, which is 0 degree Kelvin. The other thing, it has to be high volume. And the reason why is one of the postulates for the kinetic molecular theory is that gas particles do not interact with each other. Right? So gas particles have to have very, very far distances from each other, because that is the only way that they do not interact with each other. If I compress the volume into such a small space, what happens is now I will force two gas particles to interact with each other. And that violates some of the kinetic molecular theory postulates. Okay? So very, very important. And obviously, if you compress something, a gas, into a small container, you can actually make a gas into a liquid. And again, I hope that you all understand. Remember the phase diagrams that we've had before, where you have, solid, okay, liquid, gas, right? You have temperature here, you have pressure there, okay? So again, this is actually all this is rehashed again. All right, so again, ideal gas behavior is only predictable for high temperatures and high volumes. Once you decrease the temperature so low that gas particles no longer have kinetic energy, then ideal gas behavior no longer applies. They're called real gases. And if you make the volume so small that they are forced to interact with each other, that becomes a real gas.